So hello again, and now we'll see how laser measurement can reduce the price per weld. I want to show you a concrete case study, but before that, I will briefly introduce the company and present the technology and the problematic, and then we can jump to the case study. Hopefully, I'm not going to take more time that planned, but I know I have quite some slides. Yes, so for those of you who do not know MKS, MKS is a global provider of process control solution, and it is mainly active in semiconductors, industrial technology, life and science, research and defense. And it's best known for its vacuum processing solution. And in 2016, it acquired Newport, bringing to the portfolio laser solutions, motion, photonics, optics solution, and among them, Ophir. Ophir has been a leader in optics and laser beam measurement for more than 40 years now. And Ophir is split in two entities. There is Ophir Optics, which offers laser optics such as mirrors, lenses, and prism, also infrared optics for surveillance and defense. And Ophir Photonics, which is my topic here, which designs and manufactures laser power sensor that measure from picowatt to hundreds of kilowatt, and laser beam profiler that characterize beam of all shape and wavelengths. So the very first question is, why should we measure laser in the first place? Indeed, the quality of laser has become so good these days that one might wonder why it is necessary to control them at all. But they are still made of physical matter. That means that any laser is only as good as its beam delivery system, which means that components wear out and get dirty over time, and as a result, the performance suffers. We have power decreases, focus size will vary, and focus position will change. So in the end, time is wasted, scrap is produced, and money is lost. And we can see here that there is a direct link between the quality of the laser and the cost of the produced part. So this is linking it to the title of the presentation, or to reduce the price per weld. And first of all, a good laser will increase the quality with lower risk of reject, a higher reproducibility, greater traceability, and better documentation. But the efficiency will also increase. The breakdowns are avoided, or you can predict your maintenance and reduce the maintenance time. You can produce more in less time. You will consume less energy, less gas, material, and finally, less. You will do less time. You will do less testing, which is also a time-consuming part of the process. So if you know that your process is right from the laser point of view, you can reduce the testing. So there are a whole variety of laser parameters that can be controlled, but it's primarily about the process. Which process parameter is the most important? The power density at the workpiece, but it's the power per area. And these are the two main components, the power and the beam area, that we address with the measurement technology. The power density can be affected by the degradation of laser components on the one hand, and if the power degrades over time, the power per area, the power density also automatically decreases. So let's see different power measurement solutions that we have to check the power. There are many types of power sensor. The first one, they do not require any active cooling. They are passively cooled. They can come in different shape and size depending on the power to be measured and the interface to be used. Then there are the air or water-cooled ones. They allow you to measure more power or to measure for longer duration. Among these two families, there are portable and standalone solution that you can operate it with battery. They don't need any separate device to do the measurement, or solution designed to be integrated on production lines to run 24/7 on a real industrial production line, communicating with Profinet or whatever. The power variation was the easy part, so to say. Now let's move on the second important parameter, influencing the power density, which is the beam area on the workpiece. Here it gets complex. The variation can be very dynamic over time. For example, the heating of the focal optics can cause thermal lensing. This is quite common. If the focal position moves in the Z direction, the changing diameter will have a drastic effect on the area. And when the diameter is increasing by a factor of 2, the power density is automatically reduced by a factor of 4 because of the square in the formula. So to measure this parameter, we use what is called beam diagnostic or beam profiling. There are two approaches to beam diagnostic. The first option, as you see here, is a beam splitter and a camera system, or a slit-based or a pinhole system. And this system, they capture individual cross-section of the beam. Since the laser must be in contact with the instrument, the laser power is limited. Otherwise, you will damage the measurement instrument. So it provides a detailed profile of the power distribution in the beam. And to measure the entire beam caustic, the measurement system must be moved along the Z-axis and multiple cross-sections of the beam must be measured. This takes time, so dynamic effects such as the focus shift are not detectable. The second option is a camera that captures the relay scattering of the laser beam from the side. So in this case, we're not shooting with the laser on the detector. The detector is looking at the laser from the side, and we call it beam watch. It is a non-contact measurement, so therefore there is no upper power limit. You cannot damage anything. And the whole beam caustic is captured at once and can be followed live. So all parameters can be measured immediately and real time. And you can, in this case, see and track the focus shift. So now let's see the different tools available for each technology. The simpler versions measure only the beam profile. And if they die, they can be combined with some of the power meters we have seen before. Other integrates directly the power measurement in an all-in-one solution. That means these two boxes here, beam peak, beam watch AM, they are doing the beam profiling and the power measurement at the same times. And finally, among those, there are industrial version of beam watch for 24/7 measurements on the production lines, like the one you see on the bottom right, beam watch integrated. So now let's jump to the interesting use case or case study here. In that case, we're speaking of battery welding, more specifically bus bar welding, aluminum, using a 2 kilowatt single mode laser. And here you see a beam watch integrated measurement of a system with a relatively clean protective window on the optic. And this is a 7-second measurement at 2 kilowatt. So on the background, what you can see is a beam profile seen from two axes, X on the left and Y on the right. And the blue arrow, two blue arrows indicate the focus at the start, usually at the workpiece, and the green arrows are the live focus position, so in real time. So you will see that in this case, after 7 seconds, we have a focus shift of just under 3 millimeters. At the focus, where the cursor here, that is the dashed lane, you have a focus diameter of 95 micrometer, which is the expected value, and a power density of 27 megawatt per square centimeter. But at the workpiece, 3 millimeter deeper, we are out of focus. And in this case, we have a bigger beam, diameter of 112 micrometer, and a lower power density of 20 megawatt per square centimeter. So in this specific case, the effect still had an acceptable impact on the quality. That means the connectivity is still okay. But here we are speaking of a machine with a relatively clean protective window on the optic, not a brand new, but not all. So that means that from the start, the system has a focus shift. This is something to know and to take into account that you can compensate when you know it. Now, again, measurement at 2 kilowatt, again for 7 seconds, but in this case with a dirty protective window on the optic. And here you can see that we have a focus shift of 7 millimeter, as well as significant astigmatism. You can see on the orange and blue beam profile that the focus are not at the same position for X and Y. At the focus, the green arrow, where the dashed line is, we have now a focus diameter of 220 micrometer and a power density of 5 megawatt per square centimeter. And at the workpiece, the blue arrow, where the dashed line is, you now have a diameter of 254 micrometer and a power density of 4 megawatt per square centimeter. Compared to the expected 95 micrometer and 27 megawatt per square centimeter, now the diameter is 2.7 times larger and the power density is 7 times lower. So no, with that massive impact on the quality, this has a massive impact on the quality. So there is high porosity, very there could be some porosity, some bubbles, but the worst is that in this case, there is no more connectivity. The weld still looks okay, but there is no more electric connectivity. So this example shows how predictively monitoring the focus shift allows to detect the default before they are appearing. So more in the results. So we have seen that a dirty protective window increased the focus shift. This is a blue curve here, which automatically increased the focus diameter, the red curve here. And even if the weld is usually okay, as I told you, the weld depth is insufficient and we have a bad electrical connection. So that means the whole module has to be reworked, which is often not possible. So it has to be scrapped, which is quite expensive. BMWatch Integrated measures the laser after each produced part. So the measurement takes only a few seconds and is performed during loading and unloading of the part, so it is stacked neutral. It's not taking production time. Each time a pass-fail output is generated, so you can define the parameters for the pass-fail, and then you have an okay, not okay, and a detailed report is archived. So, and finally, the ability to recognize a trend is used for predictive maintenance, and the protective window is cleaned or replaced before producing bad parts. What you see here, it's like a chainsaw or like a saw, the blade of a saw, these green dots. Every time the protective glass was replaced, you can see that the focus shift is going back up. When it's going up, that means it's close to, is smaller. And then with time, it's growing, with the protective glass getting dirty. And then every time it's changed. So the limit here was fixed to 3 millimeters as an acceptable value. And every time it was approaching 3 millimeters, it was changed. So as a conclusion, so we have seen that it is very important to know and maintain the laser parameters. We have also seen that there are specialized measurement solutions that can be used to quickly measure the most critical parameters, and especially dynamic parameters such as the focus shift. And finally, we thought that the more regularly the machines are checked, the higher the quality and the productivity, which will help you reduce the price per weld. And I'd like to finish my presentation with the quotation of these two wise men. And thank you very much for your attention.
Thank you
If you have
very
any
much.
question,